Okay, let's take another example using the chain rule. Let's say we have y equals some quadratic function. Let's just say 2x squared plus 6x plus 4 raised to the power 5. And expanding something like this would take a very long time. So this is a case where you definitely want to use the chain rule. And in the last video you saw that, on the last example we saw that my variable t was equal to whatever is inside this bracket. So I'll say in this case, let's say t is equal to 2x squared plus 6x plus 4, in which case y would be equal to t to the power 5, because if everything inside this bracket is equal to t, instead of raising whatever is in here to the power 5, I can just raise t to the power 5, and that would be equal to y. Now differentiating both of these expressions, I get dt over dx would be equal to, differentiating this expression, we get 4x to the power 1 or 4x plus 6, and differentiating this one, dy over dt, differentiating y with respect to t, I get 5t to the power 4. Now I can apply, once I have an expression for dt over dx and dy over dt, I can just fill in the expression for the chain rule. So dy over dx, and remember I showed what you can do is you can write that as dy over dx, just move the dx away and fill the other two with dt and dt. And remember, this variable that I choose, I said t is equal to this. This is quite arbitrary. In some books might give it as u equals some function. In that case, your chain rule would be dy over du times du over dx. Okay, now dy over dt is equal to 5t to the power 4 times dt over dx. So that's what dy over dx is equal to. Now dt over dx is equal to 4x plus 6. So that's equal to 4x plus 6. And I just got one last step because I don't want to leave my answer in terms of t. I want to put it back into terms of x. But since t is equal to this expression here, I said that's what t is equal to. So I can rewrite this as 5 times 2x squared plus 6x plus 4 to the power 4 times 4x plus 6, and that would be my dy over dx for this expression. Okay, now you can think of all this working here as the complete working for deriving this dy over dx, but very often for functions of this type there is a very quick way of doing it, and I'll just go through, maybe take the same example and go through it. So let's say if you have y equals some function to the power of a constant. So let's say if I have y equals, I'll take an easy example. I'll take y equals 3x plus 6 and raise to, let's say, the power of 4. Then dy over dx, I can treat this function inside the bracket as you would treat x. So if you think about y equals x to the power n, dy over dx is equal to nx to the power n minus 1. That's the one we showed in the very first video. And you can treat this 3x plus 6 in the same way. And you can say, okay, let's take this power to the front. You can write this as 4 times 3x plus 6. Then reduce the power by 1, so that becomes 3. But then you got to remember to multiply this function by the derivative of what's inside. So the derivative of what's inside the bracket is actually 3. So this is, in fact, is the solution to this differential. This is the derivative of this function. And if you were to do it in show all the steps, then you would take t is equal to 3x plus 6, then write y equals t to the power 4, and then go through the working. And I would say this working here, it is quite important because I'd say it's very good to know how to derive this, because it will help you with the harder examples, and also maybe later on when you do, say, maybe differential equations and all of that. So if I was to take this same example and try this short method, so let's take y equals 2x squared plus 6x plus 4 to the power 5, and let's say I want to differentiate this. Okay, and using that method that I just shown, what you do is you take the power to the front, so you write 5 times the same function, so you have 2x squared plus 6x plus 4, reduce the power by 1 so that you get the power 5 becomes 4, but then you got to remember to multiply all of this by the derivative of what's inside this bracket, or the derivative of this function inside the bracket. So that becomes, the derivative of 2x squared is 4x, derivative of 6x is 6. And you can see you do get the same answer. And this is not only true for a polynomial raised to the power of a constant, it's true for pretty much any function. And if I was to write in a general form, let's say if I have a function raised to the power n, and this is sort of the proof that why this works. If you don't fully understand this, don't worry about it for the time being, but maybe you can do more examples and then come back to this part of the video. So let's say if I have a y equals some function raised to the power n, so then I would say whatever this function is, I'll replace that with the variable t. So let's say t is equal to fx, and if t is equal to fx, then y would be equal to t to the power n, here where n is some constant. N is some constant. So what's dt over dx? Now remember, if f is a function of x, then dt, or if t is a function of x, then dt over dx, the short way of writing that, or using the prime notation, is to say that's f prime of x. And similarly, I can say that dy over dt, y equals t to the power n, so dy over dt will be equal to n times, you bring the power to the front, then you got t times n minus 1. And then using the chain rule, we have dy over dx is equal to dy over dt times dt over dx. And remember, that is just moving the dx there, filling with dt, the basic chain rule. Then what's dy over dt? Dy over dt is this function here, or this expression. I have n times t to the power n minus 1, then times dt over dx. Dt over dx is just f dash of x, or f prime of x. Replace t with fx to give n times fx to the power n minus 1 times the derivative of fx. Okay, and this is how we get this short form notation, you could say. So if I have some function raised to the power n, and if I want to differentiate this where n is a constant, what you do is you bring the power to the front, so that's n times, you write the function as it is, reduce the power by 1, and then multiply by the derivative of whatever that function is. Multiply by the derivative of fx in this case. If you don't fully understand this part, don't worry about it, but maybe do more examples of this type, and then I think you will see how we can actually derive this for a general form. And this not only works for just a polynomial in x, it also works for pretty much, we said fx is any function in x, so fx could be any function, and this, if it's raised to a constant, then this rule would apply.